Today's topic of discussion is in regards to the encoder sensor, which is one of the core sensors that gets bundled with the depth tracking system for purposes of measuring the bit depth. What the encoder is, it is a rotary sensor. It works in rotation, and there are two flavors. There's one that's the spindle style and the one that's a hollow style encoder. They both work in the same way in that they capture the rotation of a shaft or of a cable, and then via a calibration table they're able to convert that into the movement of the bit. For today there's going to be three topics of discussion. The first one will be on the encoder direction verification, and this is the very first step that you need to take. Once you attach your encoder to the equipment, you need to verify that the direction of rotation of encoder, either clockwise or anti-clockwise, responds correctly to the movement of the traveling block, and if not, there's a way to correct that in the software. The second topic is on encoder calibration, and this is where you generate a table of numbers that will be used to convert the rotation of the encoder into linear movement of the pipe and therefore the traveling bit. So that will be our second topic, and the third one will be in regards to field mounting of the encoder. Those different scenarios where the encoder is used, and typically there are two. One is the Drawworks, which is the more popular one for land rigs and offshore rigs, and the other one is the Geolograph fixture mounting technique, and this one is used by encoder direction. So how is this done? Typically you're going to have your encoder attached, in this case, to a Drawworks drum. You can see the encoder there, and there's a shaft of the drum that goes through the encoder. The encoder housing is held stationary so that the rotation movement can be picked up by the rotating part of the encoder. You would have a rig floor, which is the bottommost position that the traveling block can go. And the way you verify the encoder direction is as follows. You'll be moving the block downwards in a downward movement pattern, and if you do that, what you're supposed to see is an increase in the encoder counts, and that will be the correct response that is expected. In this case, it is assumed that you're going to be drilling, so the counts must increase as you go down with the traveling block. The second scenario is where you're going to be going up with the traveling block, and if you do that, then the encoder counts must decrease, meaning that you're either pulling out of the hole and therefore the bit depth is going up, meaning that the bit depth is decreasing, so the number you can see there is going down. Now, if the response of the counts does not match the description here, in the sense that it's increasing on the way down and decreasing on the way up, then the reversing the encoder will be required. It will be needed, and the way this is done is in the software. You're going to see a virtual switch. In this case, it is labeled as reverse encoder direction, and if you press that switch, this will reverse the response of the count. And the animations right now, they are not linked to this particular switch illustration here. But the idea is that by pressing that switch into reverse on, it means that the response of the counts will be different, will be opposite. And that will do the trick. So that is the virtual switch for correcting the encoder direction as needed based on how the counts are responding. Right, so the second topic of discussion is in regards to calibrating the encoder. And how does this work? Here's the illustration for that. As we saw before, that's how you would mount your encoder. In this case, we are sticking with the Drawworks mounting style right there. And at the rig site, you're going to find that you have a rig floor, which is the bottommost position that the traveling block can go. And also you're going to have a topmost position, which in this case happens to be 20.62 meters. That's the top level, the topmost position that the traveling block can go. So the first step you do is to move the block to the bottommost position, and you're going to call that position number 0. Once you get to that position, you go to the software. There's going to be a wizard that you can use, and you're going to call counts for that particular position number 0, in which case right now by pressing the get start count, it will populate the counts for the position number 0 as the one that's ending here with 473. And in this case, I have chosen a 3-stage calibration. So you can see the stages are numbered right there, 1, 2, 3. And right now we're on the first stage at the very bottom position. The second step you do is you try to estimate about 1/3 travel intervals of the traveling block on the way up. And those are just approximate so that you have a reasonable separation of the movements of the traveling block. So the first position that you would go in this case is H1, and that was determined to be 6.85. And what you do, you call the counts for the 6.85 position, and you enter that number into the first stage, and the counts will have decreased further given that you're actually going up. So the number there is 6543, and the number before it was 6473. Oh, sorry, 96473. So this number is smaller if you look at the third digit there. Right, so then you would go to the second stage, and in this case it will be about 2/3 the way up, and it's always cumulative distance. And for this particular case, the stage number 2 was determined to be 10.63. If you look at 10.63 and 20, that is almost halfway there, but ideally it would be something like 2/3. But this one works as well. So what you do, you will enter your number 1063 into the table right there, and you'd call the counts for that, and there will be another smaller number. In this case is 975156. That's the count which corresponds to the cumulative distance of 10.63 from the floor of the rig. And you'll proceed to the topmost position, and in this case that was determined to be the 20.62 meters cumulative distance from the bottom of the rig floor, and you enter that and you call the counts as well, and the counts are shown here as 9960174. That's for the distance of 20.62. So for the 3-stage calibration, once you complete this procedure, you're pretty much done, and you can send this calibration table to the data acquisition system, so that it will convert the rotation of the encoder into linear movement of the traveling block. And this completes the calibration procedure for the 3-stage calibration. You could also choose to do the 4-stage and 5-stage, but the 3-stage will just work as well.